Good morning. A number of things will be rolling out this week for this class, and some things I haven't totally decided upon yet. But I'm just going to go recap, like I like to do near the end of the semester, from the calendar where we are at. We're on the 15th, and next week is Thanksgiving. So the way next week runs along is we do meet on Monday. Classes are running on Tuesday because that's the tradition of the university. But then Wednesday, Thursday, and Friday are Thanksgiving holiday break. And those 3 days match up with the Labor Day holiday that we had a long time ago. Remember when we didn't meet on a Monday and then there weren't classes on a Tuesday. So that forms a week. So my plan for next week is we'll continue to meet. I'll be talking about the exam 2 here in a few minutes. And then when we come back, we have 2 full weeks of the semester. And then we have final exam week, which for us, the final exam will be on the 13th. But for this class, and for the second exam, I mean, everything I've decided is going to be take home. So I'll be using that day of the 13th for additional lecture or discussion on the final exam that I will have already handed out at the end of the previous week. So I'll be using every time to the greatest of our abilities, and I'm not going to try to squander any time. I mean, I can goof off and you can drag me into something else that's interesting because there's so many things interesting. I'm going to try to stay on track looking at the bigger picture of where I want to get to. So where do I want to get to? I want to get through the coding theory chapter and get through convolutional codes in a particular way that at least allows you to work the final exam, which I'm using problems that I've used before. I may make changes, but basically there will be some convolutional encoding and decoding problems on there. And everything in that area works out of Scikit DSP-Com. I mean, I've got support. There's a coding theory, a CONV codes module, which supports everything that I'll want you to play with. And while neither of you came to the presentation from Zeta Associates last Thursday for the IEEE meeting, that was a very interesting talk. It was on coding theory, and it was on both block codes and convolutional codes, and then list codes, and some pretty interesting things. And the speakers, there was a speaker, and then there was another engineer from the company. I spent time, I pretty much spent about half a day with them, just walking around and talking about stuff. And I was talking to them about convolution, the fact that I do have a module for convolutional codes, and I do puncturing. And the one engineer who used to be a professor at the University of Arizona, he assured me that in his work he uses puncturing still to this day. I think of puncturing as being somewhat of an older concept, but we're going to talk about it, and that's just proof. And Joseph knows this for sure because he works for a company, that legacy is everything, right? Yeah. You just don't throw things away and say, oh, we don't do this anymore, because legacy remains and techniques still get used, and some techniques are still highly popular, and they're definitely good. So that'll be kind of our stopping point, but you'll get a chance to do some simulation experiments with that. In terms of what's going to happen before that, rather than spend the 22nd on an in-class exam, I've decided I will just give it as a take-home. It's pretty much ready to go. I may drop it onto Slack before we leave today. I'm just making a slight contemplation, and we're going to discuss that as I go through and explain what I did to get the decision feedback equalizer to work. What did I do and what did I see that I couldn't see after staring over and over again? And it's silly. I've been there before. I knew it was something silly, but I just couldn't get my brain wrapped around it enough to see it. No one's ever been there before, right? I'm saying that smiling. It's like you keep staring at the same thing and your brain doesn't quite see it. So I'll be doing that. And then there's one more assignment, set number 6, and I was studying it and realizing I can't really give it out there because it has a dependency upon one of the problems you're going to work in the second exam. So I'm just going to order your life and say you're going to do the exam problems, which are kind of like, you know, another set of homeworks, but just over a broader reach. And then I'll get the set number 6 out there. It's mostly all book problems, but there is one simulation problem at the very beginning involving gold codes, or not gold codes, but whatchamacallit, the nearest neighbor. My brain's not going to draw a blank. Well, gray codes, involves gray coding. But there's a little bit of gray coding that you're going to look at on the exam, just some numerical stuff for gray coding. And I didn't realize I had investigated that before, but it's because I wanted to figure out how to code it. And a few years ago, I wrote gray coding into some of the module, or some of the functions that are in the digital comm module. You know, I've done it before, but I needed to write it more universally, so I ended up using Wikipedia probably and Google to get some ideas on how to code something. And no one's ever done that before either, right? No. So I'll have you work on that. And then the intention of the take-home exam is that you could get it turned in by Tuesday. So the plan will be I'll discuss it some today, but if I decide I want to do something different with one of the problems, I'll maybe re-release it again. It's only going to go on Slack, so I'll give it to you on Slack today, which is just fine, right? Just like I've got a supplementary portion to Chapter 6 with more synchronization details, I'll just push that onto Slack today as well.
Tuesday is in 23?
Yes, yeah. Okay. The idea of the 23rd is you'll probably get it done pretty fast because it was designed to be mostly an in-class exam, but then I've modified it somewhat. So I'll give you the opportunity on the 22nd to ask any possible questions you might have before you actually turn it in. Meanwhile, I will get the next assignment pushed up there, set number 6, which you could be working on right now too after today's lecture, but I want to, like I said a while ago, I said I want to order your life, and I say I want to order your life to say, no, you should do this first, then do that. So does that sound good? I mean, I don't know what your boredom level is because I'm so busy that I just don't have barely a moment. It's getting...
I'm busy too, so don't worry, I'm not bored.
Okay. Are you bored? Because you always get your papers in early, and I don't know how many classes you're taking, but...
Yeah, we have some deadline for the conference paper.
Okay.
It's okay.
Okay, so...
So using 22, you'll answer questions, but it'll also be a normal lecture.
Yeah.
Also.
Yeah. Unless I feel like I'm ahead, but I don't ever feel like I get ahead because I feel like there's so many things, and that's the problem with me being near the end of my career here. I mean, you don't throw anything away hardly, you just keep building stuff up, so, and more experiences, and so on and so forth. So that's just kind of a roadmap. I think for this class, it's an easy, smooth landing into the final exam week. I don't see any glitches. I mean, my other DSP class, I see, because I have a lot more students and I have some things that they're being challenged with and maybe not always responding like I wish they would. You know, they're more procrastinating and things are going to hit harder at the end for them, unfortunately. But that's also the nature of less mature students just not thinking ahead enough. So there's really nothing else to bring up on the website right now. We'll be over here in Jupyter in a moment. Well, maybe what I should do is I should go talk about I'll talk about what I did before we jump back into fractional out-of-band power. So I pushed this onto Slack. I didn't put up a new notebook. You can just copy and paste out of that code block cell in Slack. Have you tried that ever? I mean, I'll just look at that for a quick second.
Yeah,
These cells, this is a code cell, so it's,
yeah, and it has fixed width and all that good stuff.
yeah, so you can just select out of there and just cut and paste it right into Jupyter. So I just cut and pasted that early this morning out of here, put it on, because this is my teaching tablet, not my MacBook that I do my work on. So and I verified that it builds. I mean, Shift Enter, and it does build. So what did I do? Since I've got this in Slack, I don't have the PDF here. Should be able to bring this up though. So I can point to the block diagram is what I'm going to do. Wait a minute. It's before fractionally spaced, so there it is. So I think I can magnify in here, but I'm trying to remember how I do that.
You might have to download it first.
Can you see that okay?
This is fine though, yeah.
Okay. So compared to the regular linear equalizer, which has all of those z to the minus 1 blocks with the coefficients tapped off of the input signal, which is the continuous time or sampled versions of the continuous time received signal following the matched filter, the decision feedback equalizer only puts taps for the so-called precursor coefficients. So you're going to sit ahead of the main pulse, and then the C0 there is the main pulse in the interference pattern. And then the post-cursor is managed by the decision feedback terms, which come out of what this book calls the slicer. And the slicer in my implementation is a minimum distance type hard decision rule. You see which symbol YK is closest to one of the possibilities in the alphabet. In this case, it's just plus or minus 1, but it finds the one that's closest, and that's what A hat of K is. It represents, in the notation of this book, it represents the symbol that's closest to what it sees on the input side. Then the error sequence is formed. But the feedback values are the hard decision values that come around and wrap around so that the very first input, which comes out of here instantaneously when we're making our samples over here, comes around and then gets delayed by one sample, so that it's not the present sample. You know, this is the coefficient that goes with the present sample. This one is one sample later on the timeline, which is why there's the z to the minus 1. Even though this operation of slicing happens essentially instantaneously, when you command it, it'll do it. But it has to be taken one sample late. So that's where I made my mistake. And I'll show you how I did that in the code in a second. But that's what I screwed up. What I did was I didn't put a delay in there. So I was effectively putting my D1 through DM coefficients in there on top of the C0. So my D1 was landing in the same time instant as C0 was, which the way I see it is I was hosing things up. I was having two coefficients control that point in the impulse response. Not good. You do see the minus signs on there, and that's because equation 9.8 shows that there should be a minus sign. But in my mind, I don't have to have that minus sign there, because based on the gradient descent algorithm, it will just assume a sign that it needs to drive the error to the minimum. That's my view on it. So in my code, I was putting that minus sign in there on the states but I wasn't really putting it in on the coefficients, and because those coefficients start off at 0, I don't think it really matters, and I proved that to myself. It doesn't, and in fact, it doesn't work if I put a minus sign in there. It actually diverges. It doesn't work anymore. But I had the minus sign in the wrong spot too. So now I'll show you in the code what was wrong. So we come down into the code, and I'm doing some initialization in the beginning. It's all within this DFE LMS. And the first is the constellation type, and we went over this last week. I'm only using the BPSK one. If I was doing what Joseph's going to do in his thesis, PAM4, you might use a constellation array like this. If it was QPSK, it might be a constellation array like this. So it would show the 4 possible constellation points, all at a radial value of 1, but at angles of 45, 135, or 225, 135, 225, and then minus 45 degrees. So that's one idea of something that I could do, because you asked me if I was going to do something with this now. So I could have you modify this so it works for QPSK, let's say. That would be interesting, I think. Or PAM4. I think we'll leave PAM4 for later.
Yeah.
You'll do that, or perhaps, if you want to. So I could have you do that. So then I initialize states. So I create 2 arrays, one called pre and present state. So I modified what's in that book, and I said I'm going to have n tap values as a precursor plus 1 as the on time impulse response value. And then I initialize another array to hold m zeros, and those are the post cursor values. So then I put those together into an array right here called y states. In the earlier version of the code, I don't think I was doing that, and it's because I needed to have, no, I guess I did. Let's see what I did do. That is the organization of it, though, using the horizontal stack function in NumPy. So now I start the simulation, and yeah, so I put those states together. I really didn't have to do that because I'm already doing it right down here. So this line of code, I think, probably could be removed. I don't think it means anything anymore. But at any rate, I now start processing, and I start working with the very first sample that's coming in. And so when the first sample comes into my pre and present states, I have to stack that new value onto the array and then leave the rest as empties. So if I was to go back over to Slack, what I'm doing is now I'm going to take this first value, and the very first value in that pre and present state array is this value right here. The rest of these are all zeros because the initial conditions are 0, right?
Oh,
Makes
so
sense?
Right, so you can't use LSIM because you have some steps you need to do in the middle. So you're kind of manually shifting.
Well, LSIM, you mean LSIM or LFilter?
Yeah, that's what I meant, sorry.
Okay, LSIM does continuous time system simulation with a,
That's not what I meant.
yeah, but that's an okay function, though, for controls.
Yeah.
There's a similar function in MATLAB, and you might be doing that in a control systems class. I mean, I use it too.
Yeah.
It uses
What
Euler's
what
method.
I mean is you're looping through the signal because you can't use LFilter because you have some steps you need to do in the middle, right?
With the LMS, yeah. LFilter can be used for an adaptive filter, but LFilter works best for a time invariant system where the coefficients get loaded in and they don't change. With an adaptive filter, they're changing at every step. So LFilter can be used. It's just that you're going to have to reload coefficients every time into it and then take out the states, and all that stuff. I've done it that way too. I could discuss that, or I don't know. my DSP class may be doing adaptive filters for noise canceling in their final project, and then I give that as one of the options that can be done. But yeah, I'm loading it up. So that gets loaded in there. And then notice what I'm doing is I'm shifting, I'm putting in the back half of the array, all of the past states, but I'm throwing away the oldest one. So I'm counting up, and I'm going to stop at -1, and in NumPy notation that means one index from the end. That's what the -1 means. There's also an interesting function that my DSP class is using in one of their projects. It's called roll, and NumPy has this function called roll, which takes an array and you can roll it to the right or to the left, and what roll does is it rolls the values. If you roll it to the right, it will take the values that roll off the end and brings them around to the beginning. If you roll it left, then the values that rolled off the left side come around to the back side. That can be used too, but in the case we want a shift register, so we don't want that wrapping around. So what you have to do if you wanted to roll, you would have to replace the very first value with the new value rather than the old value, and that would take another line of code, but then you wouldn't do the H stack. Both work, and all I can say to you guys is that in my DSP class I'm having them code an IIR filter using roll for the full difference equation model, and the concepts of going from the math on the page to writing it out in an algorithm, it's just painful. It's because they've never had to think that way, and they've struggled a lot, and I've struggled a lot trying to get them on board with it. That's one of the fun things about being a signal processing oriented comm systems or whatever, is you have to translate your ideas into code and then make it work. So it's fun because you have to think a little bit differently. You don't think just in terms of the math because you want to implement it efficiently. So that's how I manage the states. And then the next thing I do down here is I say, I'm now going to put in, stack it up as to one big long vector or array that has pre and present states, and it has the post states. And at this point, this is where I made my mistake. Post states still haven't been initialized. Nothing has happened because no decisions have been made. But that's okay because that's exactly what the block diagram says. I don't bring a value into here until one sample later. Likewise, I don't have any value in here initially either. So I just am fine. I will wait until I get to the bottom of the loop, and then I will load it up. So once that loads up, then I just do a dot product, or this is called a sum of products, where I'm just taking the coefficients, which were initialized up here to be 1 and 1 at the end of the pre and present array, and zeros otherwise, so that's what that is. And then I'm just going to dot it with the states. So that's the filtering action, and that would be exactly, doing all these multiplies and then summing up. That's done in that one step, because that's what the dot product would do, sum of products. Okay. And it handles complex too. So now the next thing I do is now I make my decision. So I'm working my way down the block diagram where I'm going to make a decision, and that's what this business is in here. It's taking the input sample coming out of the equalizer, and it's subtracting the constellation from it, which happens to be an array. So it's going to get the difference between what I just saw and what the possible constellation values are. And then I do this function where I'm finding the minimum of the absolute error and the arg minimum of the absolute error. And I think I put that in there to handle a special case. It seems kind of redundant, like I'm doing minimum twice, but that gives me an output Minimum always gives two outputs. It gives both the minimum error and the index where that minimum error occurs. And the index is going to point to the value in the constellation then that is my hard decision. So I load that into my post states array right here and shift that over, throwing off the old value. And now I've got the post states ready to go, but I'm not going to use it until I get all the way around and start down again. And that's going to insert a one sample delay by not using it until one iteration later. Does that make sense?
Yeah.
That's one of the things about these algorithms is you have your decision, and then things you put below might reset, initial, update states or whatever, and then all that stuff, when it comes around and gets used, the next iteration is effectively delayed by one sample. So in this case, that's exactly what I want, and that's what I did not do. I wasn't doing that correctly.
Right, it's like seeing where's the delay in this loop.
Yeah, that's right.
That makes sense.
So I do that, and then I also get the error sequence from that current value coming out of the sum of products, and then I subtract my, well, this is d hat, this is the hard decision value. It's the same as, constellation at the index that came out of this minimizing operation. This minimizing operation is handy if you're doing things with a two-dimensional constellation, because it will find the closest value in the plane, and that's what the decision is all about, the slicer is all about. Okay, so that happens, and then the next thing is I can go ahead and just in one fell swoop do the LMS update. So I take A optimum plus mu times the conjugate of the states array times the error. So this is the conjugate gradient. The conjugate times this. This is the instantaneous estimate of the gradient. And I thought that's where my error was, but I'm working with BPSK, so there shouldn't be any information on the imaginary axis that enters into the decisions. And sure enough, after I did this, whether I put conjugate on there or not, it doesn't change anything, which is nice to know, because the decisions rely upon what's on the real axis, because that constellation array just has plus and minus 1 in it. But if we go to a complex constellation, then that would be so. So it's good to leave that in there. And then I can just pass things to the output. I'm passing a variety of things to the output. They're actually getting returned into this structure array, which would be, it's a class that doesn't have any methods. It's just a structure. So DFE outputs just has placeholders for these values, so that when I pass that out of the array, I can just dot into the outputs more conveniently. It's just a cleaner way of doing it. So data structure is, I never had data structures as a class, but that's a computer science class. Is just, to me, I look at it as a way of managing things. And of course, if you put methods or functions with that structure, then you've got a full-up class that's got both the structure and the methods that operate on things, including the states that are, or the elements, fields of the class. So now that that's done, I'll just run a case, and of course this should work, but let's just see if throwing out that one line matters. It compiled just fine. Runs fine. If I just look at my coefficients, I've got 5 precursors, 1, 2, 3, 4, 5. No, never mind. 1, 2, 3, 4, 5. And then here's the 6th element. That is the central value, and that's still very close to 1. It hasn't really deviated off. And then the postcursor values are the 5 values in here, which are also fairly small. A good idea of what's going on would be if I plot the output, and just to verify this, put the dot in there, hit the tab. Those are my instance variables held in that structure. So I wanted E for the air, taking the absolute value of it because it is complex, squared, and then when I plot that, I get this. And if I wanted to drill down onto this, I could do y lim 0, 0.2 or something like that. And just see what the algorithm's doing. This would be like the learning curve in a machine learning application where it's learning where it needs to go. So it's trying to drive to the bottom of the bowl in the LMS algorithm. So that's what it's doing. If I put noise in the system, it doesn't look nearly as nice as that. It stays chaotic because the noise is in there. But with a noise-free case, this looks pretty good. If mu was too big, what would happen is out in here and beyond, it would start coming back up again, and it would start with no noise. It should go down and converge, and it should not go unstable. But if it's unstable, then that's what will happen. You want to see what that does? I think you need to have detective eyes whenever you're doing things that are adaptive like this, where things can go unstable. So if I made mu too big, pretty sure this will go unstable. Okay, it's not having a problem at that value, but if I just make it too big, no, it's still working, but I don't know. Trust me, I can make it too big and it will go unstable. It's just like a feedback control system that has now positive feedback, and it will break out. This actually looks really good, right? It's converging even tighter, so. But that doesn't look right for the eye pattern plot. So let's take this back down again. I think it may have gone off the track somehow or another. That's pretty much open. So I don't know really what's going on there, why I didn't see that in the error curve. It's finding another minimum, and it's not the correct minimum. But remember, decision feedback is a nonlinear equalizer. So I'm not as familiar at working with DFE, and then it's nonlinear behavior. But that's better than it was working with my bogus results in there. So, like I said, if I wanted to have you play with this some more, I could take one problem off the current exam 2 and put one where you maybe try QPSK out. That's an option, or I could just leave it as it is.
I did do that. I'm fine with that.
Okay.
Yeah.
Okay. Well, we can look at the exam and you can see which one I should get rid of.
Yeah. You can put on the hardest problem to replace with this one.
There's just some simple short answer questions. These are nice and easy. This is kind of an interesting one which involves optimization. I would like to leave this one in because it just makes you go back and do a minimization type of thing before. I could get rid of this one. I suppose what I should do is get rid of this one.
That was basically the homework, right?
Yeah.
We just did this problem.
Yeah, exactly. I should get rid of that one. This one is on fading. This one is just on confidence levels. Yeah, I don't know. Those two are pretty easy, but I think they're good. This one is a new one. This is based on gray coding, and it just looks at the mathematics of gray coding. This one is pretty generic. Maybe I'll get rid of two. I'll get rid of 2 problems, so that'll be worth 20 points then. And I'll just want you to get it to work, not do a lot of testing with it. This has already got hints built into it, so 9 is explained how you might do the gray coding stuff. So are you okay with that?
Yeah.
Okay.
I might ask for a little more than a week if that's okay, but I don't know.
Okay, well, I would like to have it off your chest before Thanksgiving. That would be my objective, but I could, well, set number 6 would be due, yeah, set number 6 won't be due on Monday after Thanksgiving. I think it's probably due, let's go back to this. It won't be due on the 29th. It will probably be due here, and then see, I'll be getting out the final exam, which has got some simulation aspects of it. I might even push that out as early as this time so you can just start looking it over, and then we'll have our final discussion on it if you need it on the 13th, and if you're done with it, you just give it to me and then you're done. I'm in a load of pain everywhere with grading, but it's the way it works, so. Okay, I'll do that then. Okay, I don't know if anybody did any of you find errors, or were you heading in a direction to make the code work, or you were just doing other stuff? I'm just curious.
For
The equalizer, yeah.
I work on that, and what I forget to remove the -1.
Okay,
And so it was in error.
yeah. Well, you see why the minus sign, I just said I knew I had to put I thought I had to put a minus sign in there, and then I put it on the states, but that's not the way it is in the block diagram, right?
Yeah.
You see how I screwed up?
But in block diagram, there was a minus sign before the D.
Yeah,
Yeah, and
it's down here though.
me a mistake. Yeah.
And my minus sign was changing the signs on those states.
Yeah.
That's what I did. And see, what happens is when you're trying to do the gradient descent, this-
The minus sign changes
At
your
wh-
gradient function.
yeah, but it will flip if it needs to, right? That's my thinking, is that it's just going to do whatever it needs to do its job. That's my interpretation on it.
Wouldn't you negate the derivative? So then your gradient descent formula is based on the partial derivative, right?
Yes.
So I think that it would just start running in the wrong direction. Maybe I'm wrong.
Yeah, well, I don't know. I could go back and revisit that, but I've got so much stuff to do. I don't want to work on this anymore. I'd love to work on it, and I'd love to put this into a module that goes into the package at some point soon. And I'd maybe take some help on that. But right now, we both have other things to do. So with that thought in mind, I'm not going to even push exam 2 onto Slack right now, because I'm going to change it before I do that. Just so you don't look at something and then all of a sudden I remove it and then I replace it with this other thing. So I'll try to get that out late today. That'll be my plan. Okay, so now we can go back over to this one. So we had started last week looking at power spectra and quadrature modulation techniques. And the one thing we came to was a measurement of out-of-band power, fractional out-of-band power, which is the complement of fractional in-band power. So in-band power is integrating one side of the PSD, say the positive side is shown here, from minus b/2 to plus b/2 about the carrier, and then normalizing it by the total transmit power. And the 2 is in there because there's actually a blob of spectrum up at plus the carrier and a blob at minus, right? And that's gives the total power, so that's why the 2 is in there. Since our mathematical PSD is two-sided. If you were working with a data output from a spectrum analyzer like we have in the lab, that would be a one-sided PSD, but then it's already calibrated to display everything as a one-sided spectrum. and that's the total power. So the percent out of band power is 1 minus that, and then times 100 to put it in percent. And then you get curves like this that just show you how BPSK, these are with direct pulse shape. And this is old-fashioned because it's the way SATCOM started, how slowly it rolls off. And this is where MSK really shines, and of course GMSK is even more compact. And GMSK was used for GSM in Europe. That was where it first appeared. What first appeared in Iran, by the way? GSM?
Yeah.
Okay. So just if you ever have to calculate this, and I've had to do it in a number of scenarios where you don't have a nice expression for the power spectral density, but you can run a simulation very easily. Rather than doing, trying to figure out how to do the integration, you can just do it numerically. So here I just ran MSK or MPSK for m is equal to 2 and then m is equal to 4, and then I am running down here GMSK, and remember the GMSK function, that third argument is 0 for MSK and not equal to 0 for GMSK. So I'm setting it equal to 0 here, so I run those through, and then when I want to get the fractional out-of-band power, well, I get here I get the PSDs. So those are the PSDs of those three. And if I wanted to change this to 1, then I've got the GMSK spectrum in the middle instead, if I wanted to do that. But then to get the fractional out-of-band power, I just use vector operations or array operations in NumPy, MATLAB, Julia. All the languages would let you do something very similar to this. So I'm going to have an index that I'm going to do a cumulative sum. So this cumulative sum is going to do the sum starting at 0, and this is the one-sided spectrum, and then I stop at 1 less than the end. Let me see if I can remember why I did that. This is a baseband spectrum, so length over 2, and then go up to 1 less than 1. I'm not exactly sure why I stopped at 1 from the end. But I'm accumulating just the positive half of this spectrum, so I'm going to accumulate, all the values in here. And so then the outputs are going to be growing as the vector grows, because cumulative sum returns an array, right? Rather than returning just a value, it's accumulating sum. 1 element, 2 elements, 3 elements added together, and so on as you go. So that gives you your axes, and I get my axes by taking the value that starts at 0 right here. I think maybe the reason why I eliminate the last value is because of it going to 0 or something. It's right at the folding frequency. I'm not really sure if that was the reason why I did that, but I'm doing it both for the x and the y axes. Then I can plot it. And this curve, is the same as this curve. And I put it in dB, so that's the fractional out-of-band power, and that's how many dB down it is relative to the total power. And a lot of times systems are rated at this is the baseband bandwidth, so if we wanted the the RF bandwidth, what we could do is we could just multiply by 2 everywhere on the x-axis, or if we wanted the bandwidth to be B, the bit rate, this would be the 1.0. Like this picture is already showing that. No, it doesn't. Never mind. It's the same scale here, baseband bandwidth. So you have to double it to be the RF bandwidth. So you might be curious if MSK rolls off faster, even though it has a wider main lobe. If I kick this into GMSK again, and the 0.35 is what GSM uses, this should roll off even faster still. There. Very compact spectrum, and that was the idea for GSM. They wanted to have all the carriers, this was in second generation, all the carriers packed closely together so that more users could be in the cell site. You know, GSM used time division multiple access, so each carrier frequency was shared by many users, but then when you only could put so many customers on one carrier through time division multiplexing or multiple access, and then carriers close to each other for more users to occupy that same cell. Okay, now we're going to move on in the notes to just estimating the power spectrum. I just did that simulation-wise, and the book in the notes up above here just said we'll just calculate it given the power spectral density, but I ignored something, and that is how do we get that? Well, like I've already said, simulation is convenient, and frequently that's good enough, but being able to calculate it in a closed form is nice too. So it goes back to chapter 4 when we were looking at power spectrum of a random binary pulse train. We had this model where we had the random epoch, delta, and if we're having in-phase and quadrature components like we do here, then we just have two different random epochs, and we form the complex baseband signal as D1 of t, J D2 of t, and then this is these two waveforms then in quadrature. And we have these assumptions into the model that the bits are zero mean, they're uncorrelated with themselves, and then we can go through and use another property that we looked at earlier. Take that complex baseband signal times e to the j carrier, take the real part, and that will be a Whitesand stationary signal. I don't know if you remember, but we did, it's like the modulation theorem for random processes. It could be a cosine or it could be complex sinusoid. Even though that itself is not stationary all by itself, but when it's multiplied times a Whitesand stationary process, then the mean of it will be 0, and it'll obey the properties of the modulating waveform. So we get the power spectral density using the definition in the limiting argument. Fourier transform 1, sample function, magnitude squared, and then if you break that down into the real and imaginary parts, you get the real part squared, imaginary part squared, and then we're talking about the expected value, so we're going to ensemble average over all of the random bits in the real and imaginary parts. And if we go back over to, again, what we did earlier, we'd be taking the expected value of these Fourier transforms, and the a sub k's are going to be random, the delta 1s are random, but they're uncorrelated with each other. So what happens is when you try to do the expected value here, which is down below here, you get a double sum, but then you have this uncorrelatedness between the bits. So this Kronecker delta function takes this double sum and sifts out just the diagonal elements effectively, if you want to visualize this as an n by n matrix. And this is a really cool thing that shows up in other analysis models too. I don't know if you visualize a double sum that runs from -n to +n, you could it's not an n by n matrix, I said that wrong, it's an 2n plus 1 by 2n plus 1 matrix that you're adding up the values over. That's what it's inside of here. And because the off-diagonal terms are 0, you're just adding up the elements along the diagonal, and they all have the same expected value squared. That's right up here, a squared and b squared for the different real and imaginary part components. And then the remaining piece is going to pull out is going to be the Fourier transform of the pulse shape. So where you finally get then, and then you have 2n plus 1 terms divided by 2n plus 1 terms, because this appears in both of them, the 2n plus 1, because that's the size of the square matrix, and then those cancel out, and then you get these nice formulas that tells you what the effective pulse shape or spectral shape is, and then putting it into the upshift in frequency, it's just shifting that spectrum up and down, but this is probably the most important part right here. So this is a very powerful result because it says you can handle a bunch of different cases. You could have imbalanced power, so a squared and b squared could be different. You could be modulating more in the in phase, more power, less on the quadrature. That's used in SATCOM and in some modulation schemes. I'm not sure about wireless telephony, but this result for the power spectrum holds. And it also says that if the underlying bit rates on the in phase is different from the quadrature, you'd just be superimposing spectral shapes, right? You might have a rectangle pulse shape on the in phase, raised cosine on the quadrature, and it's all there. I mean, it's in the model then for the power spectrum. You see that? I mean, this is kind of pretty powerful, I think, in terms of what you can do with it. It has some knobs that you can turn fundamentally.
PFT is the in-phase pulse shape, and QFT is the out-of-phase.
Yeah, exactly.
Okay.
Yeah. We haven't had an occasion for them to be different, but GPS, for example, which is our navigation system, satellites put up by the United States. Russia has GLONASS, and other countries have their systems, but it uses in-phase and quadrature, and it has imbalanced modulation. It doesn't have the same on the in-phase and the quadrature all the time. And there's some SATCOM standards that do that too. Going way, way, way back in time. Remember I've told you that SATCOM kind of came into existence in the 60s when satellites were first getting launched. So if we take rectangular pulse shape for BPSK, then we can just get the sinc function in there. If we go with QPSK and offset QPSK, we can just put that spectral shape in there for the rectangular pulse shape. And it's going to be a different pulse shape for for pulse shaping. Reminds me, I guess I should go back over to here and just let you know that I could have done something different here. I could have put SRC in here, right, in the simulation. Now we get much tighter spectra, and if I go ahead and do that, and it looks like I'm having log base 10 of 0. That's what the -1 was for. Now I know what was there, because I was running off the end and I was getting a value of 0 and log of that, it complains about it. And it's because of what's going on up in here. At any rate, now you see that, pulse shaping is very bandwidth efficient, but we knew that from the get-go. That's why it came into vogue for digital comms. We can control the ISI to not exist at the symbol sampling points, and we can get a very compact spectrum. And we can change it slightly by modifying beta or alpha. Remember, beta and alpha are just two different symbols used. The book uses one, my code uses another one, but so that beats out GSM. But that's not the end of the story, right? Thing you want to know about GMSK and MSK and BPSK and QPSK is their constant envelope modulation schemes. There's no deviation of the envelope as long as there's no filtering. And still with filtering, there's a minimal amount. If there's filtering, there's envelope deviations get introduced, but pulse shaping with Nyquist pulse shapes, either the raised cosine effectively end-to-end, but square root raised cosine just for the transmitter. Now there's an issue that's referred to as peak to average power ratio issues because the signal does fluctuate, and that's now the norm in cellular communications. They just broke the rules. What rules did they break? Well, the rules that they broke were in the beginning, SATCOM required and was desired to have constant envelope because of nonlinear power amplifiers in space, and they wanted to have as efficient a power amplifier as possible to save on battery and weight, and they didn't want to go with non-constant envelope. So that's why these things are still talked about. And of course, in the beginning, people didn't really know how to get pulse shapes so nicely controlled either. That DSP wasn't around in the very beginning that much. Telephone company was using it, but they weren't operating at the higher data rates. So this looks wonderful. It is wonderful, but you have to give up the constant envelope behavior to get that. You sound good? So everything has a purpose, and even the legacy systems have their reasons. But that's kind of, and of course, true raised cosine or square root raised cosine would not have either any of these side lobes. It's because it's got the underlying sinc function, which is a non-causal pulse shape, but it's been truncated, and I didn't apply any window, so the truncation has caused the side lobes to occur. But it actually would just go straight down, right? And then it's absolutely 0. Okay. Then you could bring up QAM, where you've got symbol period is log base 2m times the bit period, and then this would be even more compact spectrum as m goes above 4. So we'd have QPSK like I was just showing, but then if you went to QAM, you'd be even more compact. It would still be the sinc function for the rectangular pulse shape, but then with the raised cosine or square root raised cosine, it'd be even more compact. For MSK, we didn't go through the details of this, but there's a homework problem 925 that looks at what the underlying pulse shape is in MSK. And remember, there was just like in offset QPSK, the in-phase and quadrature were getting weighted by a half cosine. Remember when we talked about MSK, it was a half cosine, and then it was a half sine, but it was skewed by a bit period, so that ends up being a half cosine as well. So that's the underlying pulse shape right here. And then because of the technique we just went through, Fourier transform that to get the spectral shape of that half cosine, and then that can be built into the power spectral density expression. So then we get MSK's shape. GMSK would be more complicated than this because it's not the half cosine, it's the Gaussian minimum shift keyed pulse shape. So that'd be a more complicated Fourier transform.
That's a Hahn-Mundo, right? Basically.
Gaussian?
Sorry, MSK, I mean.
MSK, yeah, a half cosine. I guess that's right. But the GMSK case, and this is where I've had to do it numerically, and that's the reason why I was telling you I frequently recommend that, or I recommend that because I've had to do that. Somebody would say, I want the GMSK because I worked in that cellular environment for a while and I just did it in simulation. I didn't try to get the Fourier transform because I don't think you can get it in closed form. But for MSK you can. Okay, so our next topic is synchronization. Can't live without synchronization of some sort. We know in coherent systems we need carrier synchronization. Non-coherent systems or differentially coherent don't require carrier synchronization, but coherent ones do. And then bit and symbol synchronization is required. And then usually word synchronization, something that frames the data, is required. When we go on to spread spectrum, which we may get to late today, that requires spreading code synchronization. So just some bullet points. We want to be power efficient in almost all cases. So the first bullet says we could get rid of the carrier sync, but we lose power efficiency. So you'd have to increase your EB over N naught to overcome the losses from the simplified receiver implementation. And we've seen that already back in the previous chapter. A challenging part is there's no pure carrier present in most modulation schemes. So if you think about trying to derive a carrier from the received signal, you first have to do something to get a carrier that you can lock onto. If you think in terms of what a phase lock loop can do, it can track a tone or a sinusoidal tone in a waveform. And if there was pure carrier, some amount of pure carrier, you could attempt to create a narrowband phase lock loop that would try to lock onto it. So that's why we had in the original BPSK, there was that modulation index M. And that took some of the power away from the message or the information, but it put some pure carrier up that you could lock onto or basically filter out and have a pilot carrier, or have a carrier that you could extract from that pilot carrier and then get your coherent demodulation. And that was used or has been used in SATCOM for a long time. Fundamentally, though, you have to have some sort of phase tracking subsystem has to be implemented. It doesn't have to be a phase lock loop. There's other techniques. There's feed-forward phase tracking schemes. The talk last Thursday from Zeta, William Ryan's talk, also talked about this too a little bit, because he was talking about forward error correction using LDPC codes that can operate in very low signal to noise ratio. So he was talking about his operating point being close to 0 dB, EB over N naught. And most phase tracking algorithms need, well above 0 dB to be able to track. So he was talking about using something he called per survivor in the Viterbi algorithm when he had it wrapped up inside of convolutional coding, and that's papers that have been published years ago as well, but that's where you make the trellis in the Viterbi algorithm more complicated if you're going to have to try to do it without knowing the carrier a priori. So you just do more estimates because you don't know that parameter, or you integrate the phase tracking with the Viterbi algorithm. He didn't want us to have copies of his slides, so I can't even share that with you. He wanted us to remove them. He sent them to us for backups before he came down to give his talk, but he didn't want us to reproduce them. So, but it's out there in the literature. Not what he did, but the per survivor stuff is out there. So this is a block diagram that's in the Rice book, and I just found out a couple weeks ago, and I was looking around for something else, that he has published a second edition to that book that I mentioned at the very beginning of the semester. And I haven't gone to look for it or anything like that, but this came from that book. It's just showing you that we've had the matched filter, we have the detectors or the decision switches, these guys right in here. And these have been like a magic genie that comes along and says, just keeps going down like that, sample, sample, sample. That has to be controlled by some other means now if we don't know it a priori. So we have to have timing synchronization. Then we might, for carrier tracking, if we already have the timing synchronization, then we can come along and do this decision-directed phase detector. So the decision here does hard decisions on whatever type of modulation it is, and then we compute the phase error based on the input side versus the output side, and you can develop a heuristic or in some case a maximum likelihood estimator for the phase error, and then that can drive into a loop filter f of z, and then that can drive a direct digital synthesis oscillator, which can control the carrier frequency to drive into the inputs to the matched filter to basically stop the signal from spinning. I'm going to show you these examples because I have these things implemented in code in the synchronization module. It's also possible to avoid what we're doing right here. What we're doing right here is coming in before the matched filter, before we've made the decisions, and this is looking like an analog oscillator, so it's reaching back into the analog domain to do this portion. So it's possible to put the rotation in the DSP domain and just have a free running oscillator out there to get it down approximately to baseband, and then have your matched filter. So you're done with your analog after that free running oscillator, then you have the A to D matched filters, and then you have this rotator working in the discrete time domain. In all cases, we're worried about deriving phase error from a data-bearing signal, and one class of approaches involves a nonlinearity which strips the data modulation from the carrier, and I'm going to show you that scheme first. It's called the nth power loop, so it's an nth power law system, and if you think of memory PSK, or it can be for MQAM, the constellation shifts symmetrically. So MPSK, exactly. So if you have a constellation that can have, say, 4 different values, if you raise it to the 4th power, then it will, you know, undo that when you do that.
All of the nth roots of unity.
It's not really using the nth roots of unity, but it is effectively doing something like that. The problem with the nth power law is there's noise in here, though. So whenever you raise a signal plus noise to the nth power, you're going to generate a lot of extra noise products. You generate what are called, well, here's what you end up generating. You have, I'll just do it as an analog signal. So if you expand that out, you're going to have r to the m, n to the m, but then you're going to have the cross term in there. So you have signal times noise terms in there. And when you raise it to the nth power, you get a lot of extra stuff. But you can still set up a phase lock loop, and you can track it, and then you can divide by m, or something along those lines. So this is what's talked about in the textbook, is just raising it to the nth power and then expanding it out and go. What you're looking for is fundamentally you're looking for this. It'll be at m times the carrier frequency, but the phase is taking on states that are discrete, so when you multiply by capital M, those values are all going to be modulo 2 pi the same. So if it was pi over 4, now it's going to be 4 pi over 4. So, or if it was pi over 4 times m, and m is equal to 4, I guess, then it will be, no, it's going to be modulo 2 pi. Probably not thinking of that correctly, but multiplying by m like that is going to strip the modulation away. So you're effectively getting back.
It would be 2 pi over m times m, which is just 2 pi.
Yeah, exactly. That's what I was trying to say. So an example that I have here is for QPSK, run it through a 4th power nonlinearity. In this case, I set the SNR very high. Well, I set it to 20 dB to give some idea of the noise spectrum. So this was done in MATLAB code, but I also have it over here in Python code. So there's the QPSK signal in 20 dB signal to noise ratio. You see there's no carrier because that's the nature of PSK. It's also known as suppressed carrier modulation, just like double sideband is the earliest of the analog modulation types, but there's no carrier. Take this complex baseband signal to the 4th power, and a spike appears at DC, or whatever the frequency offset would be. There's also a lot of noise. That flat red noise spectrum is just due to the fact that we've generated so many cross terms because of the 4th power, raising it to the 4th power. So one of the homework problems that'll come out in set number 6 is just looking at some design equations that are in the book from some published papers on what is the tracking error variance associated with a second order loop that has some loop bandwidth B sub L, and depends upon whether or not you're doing a squaring or Costas loop. This is a typo in here. That should say or. If my pen will decide to start working again, and it's not. Well, I'll do it this way. It's supposed to say or squaring or Costas loop. They're both a squaring operation for BPSK, and then the quadrupling for QPSK. And what's going on here is that this is the tracking error variance, which is kind of like 1 over the loop SNR. That's the way it works out for a phase lock loop in noise. The variance of the phase error is proportional to 1 over the loop SNR. So in this case, this L is the effective number of symbols used in the phase estimate, which is another inverse relationship. If the loop bandwidth is very, very small, then you're averaging over very many symbols, and that's where L comes from. And then these terms here just represent the fact that there's more than just noise. There's noise times noise, signal times noise, and other terms that are raising up the overall floor that the loop has to operate in. And there's more terms when you're with the fourth power loop. So I've got an example in here. There's something you do in homework set number 6 with these equations. Okay. Let's just go and look at a little example, and then we'll do more of this example as we move along. So here I just took some QPSK and put in a small amount of frequency error. So this is the delta F I'm putting on relative to 10 samples per symbol in the simulation. And if I go ahead and pass it through the matched filter, after I'll pass it through the matched filter, and then I plot what those constellation points look like for a given sampling instant, it is now spinning. So if I was, let's just do this. So there's my QPSK constellation points, and then I put in a small spinning factor, and that's what we were looking at. So if we, in this case, I do have symbol sync. So this is not taking into account lack of symbol sync. I'm just looking at what goes on with the carrier phase error that actually is a small frequency error. So here what I did is I took the QPSK signal, raised it to the fourth power, and this plot of the real and imaginary parts coming out of here is just showing you that there is a sinusoid there. That's the real and imaginary parts of a complex sinusoid. It's just shifted by that 0.023. And just kind of to prove that, if that was, put a 1 in there, it still is spinning. We can't see how fast it's spinning, but here it's obviously rotating faster.
Can we see that like squared or to the third also, just for comparison?
Well, okay, you brought up a good point. What happens, this has got 4 phase states in it, so what happens if I only do squaring down here?
Right.
There's data dependency in there, right?
Less, but that's
It's still there because I'm not, and if I did it to the third power, which I don't think I've ever tried before.
probably look like garbage.
Yeah, but fourth power,
Sure.
oops, yeah, I typed something with my finger. Fourth power looks fine. I should rerun this again with a lower rate so I can see it break out more. Well, what did I do wrong? Oh, I took out a 0, that's what I did. And I guess if I put in 8, it's also going to work because I'm just now raising it to a higher power, so it's going to create a higher frequency for the phase difference. So this is 8 times the true frequency error, whereas 4 is 4 times it. But this is going to produce more noise, so it's not going to be a very good thing. So what I did here is I just used some functions that are in the sync module, and the sync module has not a lot of stuff in it, but it's got things we'll be looking at today: decision-directed carrier sync function, and it's got a non-data aided symbol sync, and then it's got some basic complex phase lock loops. So right now we're just going to use this complex baseband phase lock loop, which lets me put in a waveform, a sampling rate, decide what type of loop filter I want, and then set some coefficients, the damping factor, the natural frequency, and the gain of the effective voltage controlled oscillator. So I just added that down in here and took my waveform that's been raised to the 4th power and matched the number of samples, and that's just showing you, I'm just looking at the tracking error. It's showing you that the loop is starting from 0 initial conditions. It is pulling in and it's settling out to 0 error.
Can it lock at all with the lower power, like 1 or 2? Will it ever lock or will it get stuck?
You mean lower power or more noise?
Either. I guess like if you square this thing, can the PLL ever lock or will it get confused?
You'll get confused.
Yes.
Let's just do that. I don't think it locks.
Yeah, no, that does not lock. Okay, fair enough.
No, it's good though. These are the games. This is why I do simulation modeling, because the math only gets me so far. I can't visualize everything, and when I can start playing like this, I can do it. So now I'll take that phase error, which is the theta hat that came out down here, and apply that to this signal that I had up here. So YQPSK, I'm now going to put a minus sign in here, and I'm going to take the estimated carrier phase, which has been rotating counterclockwise, but now what I want to do is I want to counter-rotate it so it stops it from spinning, and that's what should happen here. And this pi over 4 is because the loop is going to make it lock back to 0, I want to have it go to pi over 4. So I just put in a fixed phase rotation.
I don't know why there's such a big initial error.
In the loop,
Yeah.
because of
It's
the,
trying to lock to 0 and not pi over 4.
it's just trying to lock the oscillator at 0, and I just wanted to put the points at the right spot. If I took that out of here, it would still lock. It's just not going to look as beautiful.
Sure.
It's just going to do that. We're used to seeing it the other orientation, but actually you can demodulate it that way. So I have this in here, and this is just to manage the settling time. So if I was to put that only at 10, let's say, let's see, what did I do wrong here? Had that at 70, make sure I didn't change too many things. Okay, that's good.
Oh, you changed the 70 to a 10, but didn't
Oh.
you change the recover?
No,
Then you had 2 arrays of different lengths.
yeah, that's right. What I just wanted to show you is when the loop is pulling in, then you don't have a nice looking constellation. But generally what you have in a digital comm system is you have a preamble or something for burst mode, to handle burst mode, where it acquires and settles, and then you have the starter frame delimiter that tells where the payload bits start, and then you're okay from then on if you're doing that type of communication. Okay, we're going to look at symbol synchronization next. We may finish this after the break, but symbol synchronization is done after carrier synchronization or before, it depends. What we just went through is called a non-data aided carrier synchronizer. We got carrier sync in that scheme. I didn't prove it to you, but I could go back and look at that later. If I would have made the symbols not occur synchronously, the 4th power loop can still get the carrier back without having samples at the correct location. I don't think that was obvious though, was it? I could have added some code in to do that though if I'd wanted to. And I'm going to do that in the next example, but I could have done that if I wanted to. So then the symbol synchronizing could happen afterwards. Symbol synchronization can happen either first or second as well. In the tools that I have in the Python synchronization module, I have a design or an algorithm that is non-carrier aided, so it can work without carrier synchronization being done first. This picture right here just assumes in the picture that theta is being tracked, so that my matched filter output, I just need to find the timing. The reason why I'm saying assume carrier sync is if I didn't have carrier sync, I wouldn't have a nice picture like that. If the carrier was spinning around, I wouldn't have an output eye pattern that looks like that. It would be all wrapped onto itself because it would be rotating. This is just so you can see the need for carrier or symbol sync though. So symbol sync says we'd like to get the optimum sampling times, and these pictures here come from the Rice book. I put some notes on here, but this just shows you that if you're sampling at the 2 points, 1 and 2 of the eye pattern, you're sampling once per symbol. You have knowledge of the symbol clock. You might not have it that accurately, but you have it for a short period of time. It hasn't drifted away, but instantaneously though, this is just showing you what would happen. You're not getting a very good scatter plot. It's cluttered up. So that is trying to emphasize the need for symbol sync. And symbol sync also has another mysterious, not really mysterious, but a thing that you have to remember is that maybe the crystal oscillators between the transmitter and the receiver are very stable, and I'm now thinking including mobile communication. Doppler affects all oscillators, right? The Doppler effect doesn't just go after the carrier, it goes after the clock and oscillators too, but the carrier frequencies are so high that they see the Doppler shift very quickly, whereas the symbol clock doesn't see very much shift, but it still has a drift to it that's imparted by motion. But even if you wanted to say it's not due to motion and just due to 2 oscillators, one I'll say that Joseph has, and the other one that I have, maybe it's our Apple Watches or something. The clocks in our Apple Watches are not perfectly synchronous. So things will drift ever so slowly. So the sampling of the eye pattern is not going to be fixed. It's going to change, and you're going to have to manage that with a symbol sync. The Rice book has pretty good discussions on that. You might get it from, clock might derive from a standard, say GPS. You can slave it. And cellular telephony uses GPS a lot. You could use a separate synchronization signal, a pilot clock, or have another channel that contains the clock sync information. Or you could have it embedded via a line code in the way the symbols are line coded. The most challenging one, and the one I'm going to talk about, is self-synchronization. So you have a data-bearing waveform, and you get your synchronization from that data-bearing waveform. It's like you go like this, I'm going to tough this out on my own, I'm going to do it, and drive it from the data waveform. So one early algorithm is called early late gate bit synchronizer. This one's talked about in the book, where you have this absolute value and squarer, and you integrate the early half of the bit and the late half of the bit. And this is kind of what it looks like with the data bits. So you have a gate that's sliding. Now you have to realize that the clocks aren't synchronous. You know, the gating is actually sliding along, but it's trying to grab onto the edges of the data waveform. And the early and late gate is going to give you a value that's 0 if it's perfectly aligned, as it shows here, or has got a negative error or a positive error if it goes one way or the other. So it's trying to pull it in through a clock that can be controlled digitally. And so the book Yeah.
Sorry.
This is an analog design. We're going to look at digital techniques here too. And this is where my supplemental chapter is going to come in that I haven't put on the internet, and I'm going to push it onto Slack though. I'm just trying to use as many of the notes because this is the way it used to be. And if I didn't want to use the other notes, I could get by, and then we have more time for other stuff, because right now I'm using precious time. But if this is interesting, I want to at least make you aware of it. And Joseph, this might be in what you'll be doing with the 4PAM too, since you have to lock back onto the clock, right?
Yeah, I was gonna say this is very relevant to me, but maybe not worth spending a huge amount of time on.
Yeah. This is just one technique, but it's an old one and it's a standard. And the DSP version of this is out there. But
I was gonna say, I think I've seen things like this before.
yeah, there's a number of them out there. And the other notes that I have, which comes from my synchronization or phase lock loop synchronization course material. Our book, though, does go through this. It says the timing error variance or jitter leads to these values. If it's the absolute value or if it's a square law, this is the timing jitter. And remember, early on, I'm getting close to grading that problem, but I haven't done it yet. Remember, you looked at the timing error in a non-return to zero waveform. Remember, you put the window skewed one way or the other, and you got degradation in the error probability. So this variance would be the statistical characterization of what that jitter would be. It's trying to stay right over the bit, but it's actually, kind of going back and forth like that. So if you used this value of sigma into a numerical integration of the average error probability under timing error, took the square root of that, and then that would be your standard deviation that you plug into that error probability expression that you had, then you could get the impairment or loss due to timing jitter. That makes sense? And as SNR goes down, or EB over N0 goes down, then that variance goes up. And tracking loops also have another bad behavior, and that's called cycle slipping. When the noise gets low, or high, SNR goes down, the loop will be locked, and then it will go through a chaotic event where it slips a whole cycle. So it will slip out and slip to the left or to the right, and then you lose data entirely at that point because you just had a cycle slip. And carrier tracking loops do the same thing. They slip cycles too. You generally design things so cycle slipping does not take place, but it just happens. In a digital version of this, we have something like this, where we have a discrete time version, and one early version, this is hybrid continuous discrete, where you'd have a voltage variable clock that could control the ADC sampling rate clock to get its edges such that you could always get one of the values. If it was, say, 4 samples per symbol, one of those 4 samples would always be right on the maximum I opening. But this is clunky because of the fact that you have this thing called the timing error detector, which is at the discrete time domain, but at the oversampled rate of, say, 4 samples per symbol. And then it drives a loop filter, and then it drives into a DAC, which then controls a control voltage onto a voltage-controlled clock. It sounds clunky, right?
Yeah.
But this is the way it was done for a time as we were transitioning between pure analog to pure digital.
I've seen chips that do this.
What? Put an analog?
Yeah,
Okay.
they modulate their own clocks to synchronize.
Yeah. This makes sense intuitively, doesn't it? We'll just get the DA or the ADC on board and make sure it always makes synchronous samples. It doesn't have to be one sample because the match filter needs to operate over the whole pulse shape. So we just oversample by some factor 4, 8, something like that, and then have to downsample it effectively with that switch, and that's where the timing error detector comes in. And that timing error detector could be a digital version of that early-late gate. I didn't say that, but that's coming up next. The TED is just like a little box onto itself that can do this early-late gate operation.
I imagine now you could use a Faro structure or something.
Yep, that's this guy right here.
Yeah, I think the hybrid is probably cheaper, but it also has some strange effects of like overflowing FIFOs and all that stuff.
Yeah, maybe, I don't know. But it also has analog coupling,
Yeah.
feedback, analog feedback. I mean, going back, it just seems, by today's standards, it seems crude. So this is the more modern approach where you have a fixed rate clock at the ADC, and generally it's going to be n samples per symbol. So you have T is TS over n, and it's just humming away. It's close, but it's not on, so it's drifting one way or the other, either a little bit fast, a little bit slow. Your match filter is still pretty good without having it be perfect. I mean, the match filter still applies pretty well, even if it's slipping, if it's a little bit fast, a little bit slow. But then you have an interpolator, which would be a Faro structure with using a Lagrange interpolator. And then you control that interpolator, so via the timing error detector, you can control the advance and retard of the interpolator, so it will get a sample that will always line up on the maximum eye opening. And this is a picture of what the interpolator waveforms look like. You advance a retard, and you have a base point, mu k minus 1, mu k plus 1, and then you have a shift factor where you push into your interpolator. You want to advance the timing or retard the timing, and then when the interpolator gets to the far end of its interpolation window, then it will all of a sudden, will jump to come back to the other end. It'll either jump back or jump forward, and that's handled with another waveform. So here's the interpolator, the Faro structure. Now, if I jumped over to my notes, we'd see more detail on this stuff. I may do that. We're going to take the break now. But I also have all this in a demo that I'm going to run my Python code on, so you can just see what's available in there. This is why I got into teaching the synchronization class, because being that I was an engineer in industry that worked with hardware, it wasn't good enough to look at the textbook answer of synchronization. Somebody else worries about that. I was in the mode where I had to worry about it, so I had to understand tracking loops and synchronization, and there's no better way than to be under fire. You've got to deliver something to the rest of the team, and synchronization had to be there. There was not, the textbook, leaving you without the answer, because some digital comm books just don't talk that much about synchronization. And I'm wanting to make sure you're at least aware of it. If you want to assume somebody else has got it, that's fine, but somebody's got to do it. It's not something it just takes care of itself. It has to be done. Okay, so let's take a break, and we'll come back and do some more things there. Microphone's not clipped on yet, so should be a little bit of noise as I'm clipping it on. Okay, microphone's back. We were just talking about the interpolator, and I guess since I've got it still up here, this is what makes the Faro structure so nice, is that you have this single variable mu, which is the fine control over the interpolation. So you've got sample spaced values that go into this interpolator, and those coefficients in there are fixed, and the coefficients you see in there, like the 1/6, -1/2, and so on, those allow you to do this Lagrange interpolating, and then mu is just a real variable or a real number that you can use to fine control the time delay and get it exactly to where you want it to be. And this is the cubic interpolator. The ones that I have in my library or my module are first, second, and third, so you can choose which one you want to use. The first is much, much simpler, and my experience when I worked at RT Logic, the guy that was doing the symbol synchronizers there, he would usually just use a first order interpolator, but you can go up to third order. That's pretty common as well. So I made it be programmable. So let's go over and look at that. So in order to want to study symbol synchronization, we actually have to make our waveform behave badly. So we have to mess up the synchronization on it. So I have this function called Faro resample. If I just do Shift Tab, it just tells you it represents a signal vector needing resampling or a signal vector that's perfectly sampled and you want to mess it up. So I use it both ways.
Can't you also do static phase shift with it?
Well, I have another function which I should show you because I was thinking I needed to show you that. I just did this in my other class, my DSP class. I was showing them fractional delay. So if you go down and look in here, there's this function in here called time delay. It also uses the Faro structure, as the help here says, but it turns things around. So rather than just resampling the whole array, this allows you to put in time delay that through a parameter array D. So D here can be a constant, and then it just delays every element by that amount, or it can be a time varying time delay. And this allows you to put Doppler in with a Doppler profile. So rather than it being a constant delay, you can actually screw a signal up. I say screw it up because that's what this was created for, and actually make it be a time varying Doppler, which is pretty cool. So you just put it in an array that has changes in time delay over time. And I used as a reference when I created this 2 articles. I used the article by Faro, and then I think I used another paper that was in the Signal Processing magazine at one time on the delay, on the variable delay or something. I don't know what the paper was, but both of them are published, and they were the basis for doing this. So this one is, you can also put in the audio special effect known as flanging if you want to, that was used in recording back in the early rock band era of the late 60s, early 70s, where flanging was an analog special effect where they would record in the studio, and then when they'd mix the sound back together, they were using reel-to-reel tape recorders that would play back the audio. And flanging refers to putting your hands on the reels of the tape recorder to slow down and speed up the motors. And then you can create that warping sound where you're speeding up and slowing down analog-wise. But digital flanging could be made with this time delay, where you would have a sinusoidal pattern going into little d there, and then you could slow it down and speed it up. And that actually is kind of like at a higher rate, it's like a vibrato on the audio. It's like you're wavering the tone, but if you do it in a really slow rate, and only occasionally you get that expanding or contracting sound. Have you heard, I mean, maybe you haven't heard it where you grew up, but in the United States it was used by rock musicians, the flanging effect.
Yeah, I didn't realize that was how it's made, but that makes sense.
Yeah. I used it because I was interested in creating things with variable delay. I also worked at RT Logic and helped them implement that in FPGA. I mean, and the channel simulator sits up in the lab that they donated to me that uses that algorithm stuff that I'd originally worked on. But I didn't use any algorithms fundamentally that were not already published. So I don't feel bad about having it in my Python code because I just created it from articles that were already public. You know, whether or not they have a patent on it or anything, I don't think you can get a patent on this because it was published quite a long time ago. And another thing I guess I'll point out is that in the newest version of the code, D here is little d, but when my co-author was doing things, he didn't change everything in the help. So if you have d equals something in here, you've got to make sure it's little d, otherwise it's going to give you an error. So in the resample now, what I'm going to do is create a waveform that needs to be sampled. So I'm doing a small amount of timing change. I'm assuming the input clock is 1.001 and then the output clock is 1. So I'm doing what? Am I making the samples closer together or further apart? The output clock is slower than the input clock, so the samples
Yeah, you make it
further apart because I'm clocking it now slower by a small amount. And then I go through a matched filter, and then I go into this function called non-data aided symbol synchronizer, which has some parameters in it, a time bandwidth product parameter. This came from a paper motivated by the Rice book, and also another paper. I guess I don't have that one referenced in here. It was motivated by the Rice book, but he had it in M code. I put it in Python, and also the way of getting the timing error detector is something that I did that he did not have in his book. I don't know why. There's something about the book that was like, he did a lot of great things, but then he didn't do one fundamental thing, and that was give you the way of doing the timing error detector that would function properly in a real environment. So I ended up getting that from another book or another paper. So here I'm putting in some parameters. See, what's the third one? Nominal number of samples per symbol is going to be 4 here. Time bandwidth product, the tracking loop is the next parameter, so that's 0.002. And then I'm asking for the feedback control system tracking loop to have a damping factor of 0.707, and the last one is the order of the interpolator, 1, 2, or 3. So I've chosen 3. So I already ran it, and I have it output the synchronized waveform, sample once per symbol now. So this will not output a waveform. This outputs just once per symbol. I can do a scatter plot with it. And then it also outputs the error signal, so I can just see down below here that the loop has gone through a quick transient. That little fast spiky thing is just some initial condition that is before it even gets up and running. It just has to manage some transient, but that other lower frequency undershoot there and then settling is the loop pulling in. And then because of the data dependency on the symbol tracking, there is some jitter on it. I mean, there's data related jitter in a tracking loop too. It's not just due to noise, there's due to the data patterns, and that's why people will talk about tracking algorithms and what's the density of the transitions. Most tracking algorithms, if you take away, well, just take a baseband waveform like NRZ waveform. If it was all ones, it would just be high or -1. Can you get a clock out of that? No, you don't have any transitions, you can't get it. So there's
You mean like scrambling, like XORing your data with the PRNG so you get enough transition?
yeah, exactly.
And then de-scrambling at the receiver.
Right.
And you get like DC balance lines and all that fun stuff.
Yeah, things related to that, but there has to be transition. So that's why there's some jitter on there, even though there's no noise. It's due to the the random data bits that I've got going in the system. So now I can take that and go through and do the scatter plot, and I'm starting, if I started at 1,000, let's say, we can go up here and look, and we can see this at 1,000, it's just barely gotten locked up. So this seems very inefficient. It's taking about 1,000 symbols to get locked up, which seems like a really long time. It's just I've got it a very narrow bandwidth so that it can reject the. So I guess I didn't make that small enough. Make that 500. And we're seeing the impact of it not having settled on the symbol sync, so it's not sampling the eye at the right spot initially. It's getting close, but then as it cruises out there, so arbitrarily I set this at 2,000 just so I could see that we were already settled. Okay, so now let's take it up one more level. This is not in the notes, it's in my other bonus chapter, I guess. So now we're going to do this NDA symbol sync, so non-data aided, and that's what this means. You don't need to know the data, don't need to have estimates of the data, and what that means, I was using the wrong term before the break, but NDA means no knowledge of the data. I won't have knowledge of the data until I get the carrier locked up too, and then I can actually make hard decisions on the data. So this algorithm is an amazing algorithm that carrier doesn't have to be there either. I don't have to have knowledge of the data. I can actually find the edges on BPSK, QPSK, MQAM, or anything. You can find transitions from any of those waveform types. And you don't have to have the carrier done first. So that's one of the cool things about this algorithm. So now what I'm going to do is I'm going to Faro resample like I was doing before, and then rolled up inside of here I'm going to put in a small amount of frequency error as well. So the signal is going to be spinning and the samples are asynchronous. Sound like fun? So I do that, go through the match filter, and then I do the NDA symbol sync, and it's running over 10,000 samples, and then I look at the scatter plot, and I say, it looks good. Why does it look good? Because I've gotten the symbols sync back. I have a nice circle, so at least I know I have the symbols sampling back because it's staying on a nice full radius circle. If it was not syncing, if I was not able to make that happen, like suppose I make this too big so the loop can't track it, make the resampling clock too big, then I get more of a donut. It's not actually being able to synchronize to it. See that? It's just like, I can't find it. And I could make the loop bandwidth wider and it might be able to find it. I'm not going to mess around with that, but is this making sense though?
Yeah.
So I got to change this back to.
You're saying symbol synchronization is basically like the radial spread, and then carrier synchronization is like the
Angle.
angle, right?
Yeah, so have that. And now I come down here and I have another type of carrier sync. This will be a decision-directed carrier sync. This is like the one in the earlier block diagram. This is not using a fourth power loop or anything like that. What it's doing is it's doing this, finding the angle heuristically, or actually there's several algorithms inside of here at this point. There's options that are available. Again, motivated by the Rice book, but there's several different algorithms that are available in here. So type can be equal to different things. And these are things that talk about in that other class. So type 0 is what I'm using. So it takes the one sample per symbol that comes out of the symbol sink, and then I get the error signal out of here. So why does this look kind of funky? It's because in the very first part of the waveform, there's no symbol sync. So it's getting, it's not synchronized yet, symbol-wise. So this decision-directed algorithm cannot estimate any bits, and the bits are decision-directed just like they were in the DFE and in the decision-directed equalizer. So it's just sort of confused at that point. But then as soon as the symbol sync is locked, which remember was almost at 1,000 symbols, now this decision-directed carrier loop can lock up and pull in and drive down to some jitter. And then finally, when I go make this picture over here, I'm there at 2,000, so it's not really pulled in. If I was to increase this up to 4,000, then it's getting pretty tight looking because I've pulled both tracking loops in. I don't know if this is exciting. To me, it's very exciting because it's working, and it's not trivial. I mean, you have to do these things. So when I had this class ages and ages ago, never talked about any of this stuff, never tried to do any of it, just faked it, which you can do in the computer, right? You can make the Magic Genie signal do everything. But the key to doing this was when I worked at Atmel, which is now Microchip, I had to work on a Zigbee radio algorithms package for the ASIC they were designing. It was an RF CMOS chip that had digital on it. So things that I didn't have at that time, I always had this ability to put in frequency error with a complex exponential, but I didn't have this Faro resample function. So when I worked there is when I created the needs. I was doing it in MATLAB, but is when I needed to do this. And then, so I had to create a means to screw up a signal because I needed to have test vectors that could test the robustness under clock errors. And in that work, they told me what the parts per million of the crystal clock oscillators that were part of this IEEE standard, 802.15.4, and it has embedded in that standard what is the ppm on the clock oscillators, parts per million accuracy. So I had to be able to pull in and track a signal that had so many parts per million. So need necessitates developing more software tools. So what I like about it is you generally don't want to do that when you're first learning a subject, but when you want to understand how you really do it, then you can do that stuff.
Does that symbol synchronization, or do any of these deal with like the 4 Ys, phase ambiguity and QPSK, or is that?
No, they don't. So it'll come out with an ambiguity error.
Right. I guess that's what word synchronization does.
Yeah, or we could have differential encoding, and that could help too, but and that's why we talked about that. But yeah, word synchronization will help with that. In the system I was working on, I only worked on one of the most lowly Zigbee standards, and that was the one that used BPSK. The one that was also alongside of it was MSK, but the BPSK one just had, you know, NRZ data bits, and there was a starter frame delimiter that you had to look for right after you got locked up, and that would just, and there was also a spreading code on it too, a fixed spreading pattern, and that, yeah, I guess that's how I did it, was with the spreading pattern, because that pattern was either right side up, which is part of a Barker code, which was used in the original Wi-Fi. So that was part of that, I think. That's where I actually did something that was really novel, and I would like to have written a paper on that, a journal paper, because I think the way I had to process the signals in that, for that project, because of the way the ASIC was developed, but I would have to get some sort of rights or permissions to do it because it used proprietary, I mean, it was a proprietary thing, and I just elected not to go off and do it. But I think it was pretty novel what I came up with. It was a two-dimensional search is what I had it do. I don't know. I was really excited at the time. I thought it was cool the way it worked. And that's the thing about your life. You will do things that you can't tell anybody about because it's a trade secret. And if it's government work, it's a government secret, but you still have secrets no matter who you work for that you have. You know it, your team knows it, but you can't tell the world about it. So you just have to, I don't know, smile about it. It worked, and go on to your next problem. Before I do that, I just want to jump over and see what is in here, if there's anything. This starts off more generically for the phase-locked loops class. These are different pictures, but they're similar types of things. This is the book, though, that my symbol sync algorithm we were just playing with has as the timing error detector. It uses an algorithm out of this book. And
You said you're going to send us that, correct?
yeah, I'll put it on Slack if you'd like to have it. It's not a problem for me. This book number 2, oops, don't have the pen on right now. This is another book. I don't know if you, I wasn't doing that. I don't know what's going on here with this thing. It's in a bad mode, but at any rate, number 2 there, Umberto Mengali and Andre. There's a couple of Italian guys. Their book was published in 1997. That other book by this guy's name again. I used to have these things loaded in my brain. Meyer. I used to use Meyer's phase-locked loops book, and then he wrote that other book. These are classics for me. This one, I really, really like this one. This one is in some ways better than the Meyer book, but both of these are really good for synchronization. They're old now, but they were all digital modern techniques that were talked about in the books. And this book by Mengali, I used to check out of the library and keep it checked out almost all the time. The price just kept going up and up and up on it, and I finally broke down quite a number of years ago now and bought one for like $250. It's probably $400 or something crazy like that right now.
No.
Because it's just, there's never quite been anything else that has gone through the synchronization techniques for digital receivers as well.
And it's out of print.
I don't think it's out of print. It's just very expensive. It might be out of print now. I don't know. Both of these, though, and this one, like I said, this is very good. They came out at about the same time. Meyer is German. I think Monoclet is, what's the other country that's close to Germany? I'm thinking of, does anybody, do you recognize the nationality from that last name? I'm trying to think. I used to read his papers a bunch too. These guys are probably retired now. I'm trying to think, what is the other country right there in that part of Europe?
Belgium.
Might be Belgium, but I don't know. Both of these authors are Monoclet, and then the first and last are Germans, but Monoclet is from another country close by. So these are things we've already talked about. A few more pictures from the books that I put in here. We didn't talk about this, though, so I'll just mention this one. We talked about the nth power digital phase-locked loop. This is another technique, though, that both of the books talk about. And this technique was actually the NDA feed-forward phase synchronizer. Viterbi and his daughter, who's also a PhD in electrical engineering, published a paper on this one. So I latched onto this and used this in the algorithm for the carrier sync that I was doing at Atmel when I worked on that Zigbee 802.15.4 standard. And the way this one works, this takes the raw signal and you have a possibility of a nonlinearity on the magnitude, and then you take the angle, which you get from the arc function or four-quadrant arctangent, and you multiply it by m. So this is very similar to the mth power loop, but this doesn't have a feedback loop. This is feed forward. So what you're then doing is you're going to do something on the magnitude independent of the angle, put it back together as a complex signal, and then you smooth this with a moving average FIR filter, and then you can take the argument and divide by m to get the angle estimate back, and then you've got a conjugate thrown in here, which I didn't show, so that this e to the j theta hat is going to be the opposite of the theta phase rotation that's on there, and then this can work, and this is no tracking loop, so this can be very good for burst mode communications, and that's why I used it in the Zigbee radio, because I wanted it to be fast, because the preamble wasn't very long. It works well. I've had projects in this class probably that look at it, or the phase lock loop class that I've looked at doing this. I wrote an educational paper on both of these techniques being used in a introductory class in digital comms or phase lock loops, and that's hanging on my wall of my office. It's a really old paper, but it was just trying to get people thinking about synchronization at a younger age. This we did. We saw this. This is the heuristic carrier phase. We saw that. That's what the error looks like. In all of the tracking loop algorithms, we have to have a numerically controlled oscillator, and then you have to be able to relate the parameters of this numerically controlled oscillator, loop filter, into second order analog loop filter. And a second order analog loop filter would have a noise bandwidth in hertz, Bn, and would have a damping factor. So these equations tell you how to set up your digital loop filter. These are some other types of decision-directed carrier phase. And then we saw this for the timing synchronization. And this is what the error signal looks like from a couple of other types of timing error detectors, which are talked about in the Rice book, but here the early late is also talked about in here. So this picture, didn't see these pictures of the polyphase, and then this is also in the Rice book, the interpolation control, how you actually have to write your code, which is in my module, to control the interpolator. There's an underflow and a modulo 1 register, and then there's mu that comes out of the tracking loop part, but then there's also this underflow, and that's kind of one of the secrets to getting this thing to work properly. This is kind of tricky. I'd never tackled it until I saw his book and saw how he coded it in MATLAB code, how to get this register stuff to work properly. And that's what allows this thing to happen, that sawtooth wave where it has to wrap at the ends with that underflow and then the mu part. So this is tricky stuff. I've never actually had anybody write this. I've just given it to them because I figured I studied the code and then I implemented it and did it in Python eventually. So this just shows you a little bit more what it looks like when it's all put together. But the timing error detector is what I implemented, because this algorithm in his book assumes carrier phase is already present. It's just silly. Here's match filter and derivative match filter for doing the timing error detector, but his was data dependent. So I still disconnected on that. It's like you take his book and it's beautiful, but it's missing, it's got some holes. It's like you can't do certain things. So I pushed it further to be able to do it. And this is what that NDA by spectral estimation from the Meyer book. So this is what I'm implementing behind the scenes in my code, the NDA stuff. And then I played with that when I was working on it to get it working, and originally it was working in M code when these notes were written, and then it was in Python code. And I guess there's a whole lot more in here. I don't know what else is in here. Oh, some examples. There's a bunch of examples. So I'll push this on to you and you can have it to look at then. Sound okay? I'm not going to put it on the website. I'd rather not do that because it's a lot of stuff from the book, but as long as you have a copy of it, that's good, right?
Yep.
This shows up in my other class, the phase lock loops class, so that'll handle that. So we have word synchronization. There's different types of word synchronization. Marker codes, the book talks about self-synchronization. I'm not really big on this myself because I definitely haven't studied it. The things I've seen before are like Barker codes or some simple code that you can use for starter frame delimiting. He introduced marker codes in the book more recently, and I looked at them. Again, I'm not an expert on symbol sync codes or frame sync codes, word synchronization, but it involves correlation. It's like anything. It's done as a digital correlator, though, and then you can find where it starts. So I attempted to write something in M code, playing around with them, but I don't want to talk about it because I'm not really that knowledgeable of it. It is what it is, though. It's some short-length code that's good at having low cross-correlation. That's the really main thing about any sync code. It's going to be possible to have any sync code you create appear in nature, as a random bit pattern, and that will confuse the ability to sync. But if you design these marker codes or any word sync codes properly, you can minimize the side lobes. You can never make it impossible to lock. You'll just lower the probability way down that you won't see it. You won't have a false lock. And that's what these patterns are looking at. This is just all possible patterns of random bits, and then you're seeing where it's hitting and finding the pattern of interest. And PN sequences can be used for that too. So I am pretty fond of pseudo-noise sequences, or PN, and the type that I'm most familiar with is the maximal length PN sequences, or pseudo-noise sequences, and they are talked about. Pardon me?
Those are gold codes, right?
Gold code is a special combination of two PN sequences XOR together. That creates the family of gold codes. So they're separate. A gold code, though, was developed from the M sequence model.
Okay.
If I taught the spread spectrum class, which Roger Zemer has a book that he wrote with two other authors on that, then we go into a lot of detail about gold codes and more on M sequences. And I think the guy's name was Richard Gold. I may have the first name wrong, but he's the inventor of the gold codes, and gold codes have shown up in a lot of different places. They were popular in CDMA originally, and I think maybe 5G. I don't know. Does 5G use a gold code for anything anymore?
I don't know.
Yeah.
I know we sometimes use gold codes to make pseudo-random numbers.
Yeah, it's a repeating pattern, just like an M sequence is, but what's special about the gold codes are, and they're used in the GPS satellites, they're used for course acquisition. The gold codes, like in GPS, you have a 1023-bit long pattern, and it's the 1023-bit long gold code. You can create a number of gold codes that all have the same low cross-correlation properties.
Yep.
So that's what's good about the gold code. They can all be the same length, 1023, but the codes are different so that you can use them for multiple access communications, and that's what GPS does. GPS is a multiple access system where each satellite has its own gold code, and that's how it's separated from another signal. And the gold codes let you do that at the course acquisition level. Then there's the fine code, which is used for precision correlation and precision navigation, of which we don't do for the public. That's in the classified system, the fine code. But the coarse code, or CA code, is a gold code. And that's how all our devices geolocate, in the US at least. So a little discussion on that. Three-stage shift register, just as a starting point. What is an M sequence? It's a feedback shift register where you have an exclusive OR between two or more taps, and you use that to form a feedback. So in this three-stage register, this particular implementation of the gold code of the M sequence is stage 3 XORed with stage 2 fed back into stage 1. And generally when comms people talk about gold codes, they're talking about logic levels 0 and 1, but then the waveform itself is actually translated to be plus and minus 1, because that's how it fits in with the rest of our antipodal signaling and NRZ and so on. But it can be implemented in digital logic using zeros and ones. In my real-time DSP class that I teach in the spring, gold codes gold codes have been used in that class too, but just PN codes, you implement it in C, and you can do it very efficiently with a single, say a 16-bit integer, and then you can do all the bit manipulations in right shift and left shift and hold your shift register just in one 16-bit integer, and then you can handle up to 16-bit long patterns, and then you just code it all like that. This is the property of the M sequence. If it's a maximal length PN code, it will have this for its autocorrelation function and this for its power spectral density. Proving this is not super easy, but it is done in the spread spectrum book. I'm pretty sure how you can come up with that. There's some interesting properties of M sequences. And the autocorrelation function is periodic, obviously. Its length, the code period length, is always 2 to the n minus 1. The spectral peak occurs once per period, and if it's a waveform, it's going to be triangular. If it's just the sequence, it's just going to be not triangular. It's just going to be sample values. But the property is when you're not on the correlation peak, you're always going to be at minus 1 over n, whereas when you're on the peak, it's at 1. So the property of the gold codes, I think, yeah, it looks like that. If you're looking at it as a continuous waveform, or if it was a discrete waveform, you'd just be seeing it happen like that. But if it was an analog waveform, it would take on two values, 1 when you're perfectly aligned, and then minus 1 over n when you're not aligned. And that's one of the properties. There's other properties I don't have in here, but they're in the spread spectrum book. And when I have students do labs in the COM1 class, they do things where they look at the M sequence. An M sequence, if it's got a shift register of n bits long, there always is going to be one pattern of n ones. There'll be a pattern of n minus 1 ones all the way down. So you're going to see occurrences of these subpatterns in an M sequence. But one of the things is you're always going to see a pattern of all ones, n ones. If you were to see a pattern of n zeros, the shift register would stop, because it can't function then. So you've got to have it filled up with some ones. In my early life as an analog, or analog and digital logic together, I built high-speed PN code generators, and we had to have a means of starting them by inserting a few ones, and then that startup circuit would go away after it's up and running to make sure it would always run. Have you been there before?
Yep.
Okay.
So I was realizing, so
Okay.
choice is you add a number from 0 to 1.5, right, and then round.
Mm-hmm.
And so we use very long gold codes for that, so that we don't have any autocorrelation in our rounding.
Okay. That makes sense. You want to be very precise.
Well, yeah, well, because you don't want autocorrelation in your rounding, because then, yeah, you get nonlinear, you get data-dependent rounding, right?
Right.
So anyway, but yeah, we do things like that where, yeah, we have to kick it off at some point, and yeah.
This is the spectrum. The spectrum is a line spectrum because it's a periodic signal, so the power spectral density is not continuous. Power spectral density would be continuous if it was a purely random bit stream, but if it's a pseudo-random bit stream, which was what PN stands for, pseudo-random noise, it will have a spectral line, and the property of it is that the minimum spacing on the lines is always going to be f clock over two to the n minus 1. So that'll be the minimum line spacing. You divide by the period, which is 2 to the n minus 1. So this is some MATLAB code, but you know, I've never been a person that wanted to just be content with my Python exploration. So if you go into Python and you just go into the Signals and Systems module, I've got functions in there because that was something that I've always done in my teaching, is had students learn about PN sequences. So if you go down in here, there's this function, PN generator, which just creates bits. So it just creates like 2 to the m minus 1 bits. So if I was to do that, no, this does it continuously. No, never mind. So if I do 10 and I just say do 3, there's the PN pattern, and if it's 3 bits long, it's 2 to the 3, which is 8 minus 1. So 1, 2, 3, 4, 5, 6, 7, and then it starts over again. So this can be used as a data source, and then I could upsample this and do other things with it if I wanted to. But then another function that's in here that involves PN codes is, at least I think it's in here. I may be getting this confused. Maybe it's not in here. I thought I had the fundamental function that just creates, yeah, there it is, M sequence. So we have M sequence. An M sequence just creates the one period. So if I put in, I can put in 2, 3 up to 12, and when I was on my sabbatical, that one year when I was writing this, they wanted it to have 16, so I put in a 16 in there too. So if I was to do 16, it's not listing but a few of the values, but that's going to be 2 to the 16th minus 1 values before it repeats. If I was to put in like 5, then that's the whole period, the PN pattern. And I've had people from other places say that's not the real PN sequence. So this is just an interesting comment. First off, you can see my generators start off with that pattern of the 5 1s, or you know, n 1s, and then you can see, if you look through it, you'll see an occurrence of 3 1s. I thought there was an occurrence of 4 1s in here, but I don't see it. But this person I used to work with at Cosmic, he said, your PN generator's not correct. Well, there's no exact right PN code. It can be, this is a 5-bit code, but it can be flipped over. It could start in a different spot in the pattern, but you've got those two options. You can run it forwards or backwards. So.
And also, you can use these to XOR them with data to get more bit transitions, right?
Yeah. So I mean, just an example, in Python, if I wanted to run it backwards, I can just flip it around by just concatenating that operator. The third argument in the colons there is just making it step backwards, whatever. So, okay. So M sequences are useful as a starting point for spread spectrum, and PN codes, or actually gold codes are used in GPS. So this is the beginning of the spread spectrum section. I've got about 4 minutes. But do I want to do this? I could go off and look at some notes. It's a nice simulation project for the M sequence. Let's just do this for a few minutes, and we'll have to come back to this. So what's good about spread spectrum, and what is it? It's a modulation scheme that provides, resistance to intentional or unintentional jamming. And intentional would be in multiple access. Provide a means to spread the energy density over a wider band of frequencies. And this is where it's been used in certain types of radio standards where the FCC says you can't put all that power in that narrow band of frequencies because it's going to be shared by another user, so they'll choose to spread it out over a wider band of frequencies. And spreading in general is used by ultra-wideband communications to spread it out over a very wide bandwidth, so many people can be using ultra-wideband with different spreading codes and coexist. There's a standard that was proposed for replacement for Wi-Fi. It's still rumbling around out there, and it's actually in 5G, right? There's an UWB portion of 5G. I don't have my phone does it, but I don't ever find a hotspot or anything where I can use it. But my brother-in-law has a Verizon phone, and he can get ultra-wideband through the 5G in some spots. Any of you ever noticed that you've gotten super wide, high throughput through UWB?
I didn't think I found that here.
Yeah, I haven't, but that's what he tells me. Provide resistance to multipath. And then multiple access, which I already mentioned under 2. And in GPS, it provides a means for measuring range. And in satellite comms in general, most satellites do have to do ranging as part of their mission. So they are doing ranging, and they're generally doing it with some pseudo-random code. There's 2 main types of spread spectrum. One is direct sequence, and direct sequence, you're just going to multiply your data source by the spreading code waveform. It's clocked at a much higher rate than the data source, so it's going to make the data pattern coming out look like it's at a higher bit rate. A second type is frequency hopping, and like I said, Bluetooth, I've said that before, Bluetooth uses frequency hopping. GSM, the European system, uses frequency hopping. It's where you just hop the carrier frequency around with a pseudo-random hopping pattern. So the way spread spectrum fundamentally works, and this is where I'm going to have to stop, how it gets some of its main properties are when the signal comes in, and this is out of the book, that picture on the far left says that you've got a wideband signal, which is the triangle, and then you've got noise stacked on top of it. And the spread spectrum signal can actually sit below the noise floor, and you don't even know that it's there. That's the nature of UWB. You're not supposed to know it's there. It's not supposed to interfere with anything, like GPS, for example. And then you have the local code that comes along at the receiver, and it will be synchronous with the spreading code once you lock onto it with a despreading algorithm. And it will take that spread signal and it collapses it down, so you get Um, this action of it popping up out of the noise. Because it correlates, it wipes off that spreading code pattern, and it's now down to these symbols or bits that have a very large period relative to the spreading code rate, or chipping rate is what it's called. So it can pop up out of the noise, and the interference, which was perhaps a narrowband jammer or some other type of signal, is getting spread when you're despreading. So when you despread, you bring your signal, collapse it down, and it can pop up out of the noise. The interfering signal gets further spread or just looks like noise. So that's kind of two of the basic things. And then carrier can be obtained and symbol sync can be obtained later. But usually the despreader can also be related to the symbol sync. The system I worked on for Zigbee, once I got the despreading done, then I also had a symbol rate clock available, and the carrier was done in front of it. The order of things can be different, but frequently you have to despread first because the signal to noise ratio is so poor that that's the only option you have. You can't get a carrier track going and can't get the bit sync going, because you got to be able to get the signal above the noise floor. Sound interesting? Third generation cellular used CDMA exclusively. I mean, the CDMA part of third generation did. So we'll talk about that some more next time. We're eventually, though, going to get out of that, and then we're going to go through multiple axes. But kind of our big stopping point here that I have to get to is get into OFDM, and we'll get into OFDM, and then you'll have OFDM also on your final exam where you're going to play with OFDM, and that's in the digital comm module. I have some OFDM pieces in there.